Hello, future scientists. In this grade 12 chemistry tutorial on solution equilibrium, I'm going to show you how to do a problem most of my students have trouble with, and that is determining whether or not a precipitate will form when two solutions are mixed together. Let's get started. All right, so I'm going to go through this step by step, explaining each step, what we're doing, and most importantly, why we're doing it. A question like this can be done very quickly, very short. There are lots of shortcuts to doing it, but I'm not going to do any of those. So let's go through it step by step. Question says, will a precipitate form when we have a 50 milliliter, so imagine this is a beaker, a 50 milliliter of a 0.5 mole per liter solution of lead 2 nitrate is mixed with a, is our other beaker, 25 milliliters of a 0.025 mole per liter sodium iodine solution. So let's first start to think of this as a grade 11 problem. In a grade 11 problem, we write out the double displacement reaction and try to figure out what the precipitate actually is, if there is one. So let's start doing that so that we can understand the problem a bit better. So we have Pb NO3 2 plus sodium iodide. These are both aqueous solutions. And that's going to give us, this is a double displacement reaction, so let's have sodium nitrate. So NaNO3 plus lead 2 iodide. So PbI2. And then in grade 11, you would need to look at your solubility tables to determine whether or not this would be aqueous or solid. Okay, so you can look up your solubility tables, and you might remember that nitrate is highly soluble with pretty much everything. So this is going to be aqueous. Iodine is highly soluble with many things, but they have some exceptions, and lead is one of them. So this is going to be our precipitate. So this is what we're going to be interested in for this problem. Now in grade 12, the question becomes not whether or not we can identify what the precipitate would be, but whether or not we have enough of those solutions to actually form that precipitate. Because if you look at your solubility table, it simply says this has low solubility. It doesn't say it's insoluble. So some can dissolve. So do we have enough to actually exceed the saturation point to supersaturation to form a precipitate? So let's go ahead and write this out as our solubility equilibrium. So we got lead 2 iodide is in a solubility equilibrium with its ions. So we've got our lead ion and our iodine ion. Now, a question I get a lot is, why is this not I2? It's a diatomic molecule, isn't it? Yes, iodine is a diatomic molecule when we have, say, iodine gas, but this is the dissociation of an ionic compound into its ions in a solvent, in this case, water. So we have our ion iodine -1 charge. It's not going to be I2, so to balance the equation, we need the 2 in front as a coefficient. Now, we can also set up our ice chart. We don't need to for this question, but to help you sort of understand where we're going, I'll set that up. Now, solids or pure liquids, we don't consider in our equilibrium law because their concentrations are constant. They're not changing, so those values are included with the equilibrium constant. So we're not going to look at any of that. Problem is, I don't know what our initial concentrations are. So let's figure out what those would be and how we're going to do it. So first we have this solution. So let's just look at that solution separately. So I'm just going to use this space over here in a different color. So we have Pb NO3. Oh, Yes. 2 dissociates into its ions Pb plus 2NO3 aqueous. Okay, this, remember, is the ion we're interested in, right? Or one of the ions we're interested in. Now our coefficients are 1 to 1, okay, for our solution here. But here's the thing. If I have this solution and our other solution, which is sodium iodide, so let's write that out. So sodium iodide dissolves to give us sodium ions and iodine ions. Okay, here's the other one we're interested in, our iodine ions. This is also a 1-to-1 ratio. So we have the one solution and the other solution, we mix them together. So here's the thing. We're given a certain concentration for this volume. And for our other solution, we're given a certain concentration for its volume. But once we mix them together, the volumes have changed. So we need to figure out what the new concentrations are, specifically for these ions, because those are the ones that we're interested in here on our ice chart. So I'm going to erase this, but remember for now, these are 1-to-1 ratios for our molar ratios. So let's start with lead. Concentration of lead. We're looking at initial here. So initially, concentration is moles per volume. We're given concentration and we're given volume. So I'm just going to solve for how many moles of that ion we have. Or in this case, we're solving for how many moles of lead 2 nitrate we have. So we're going to take concentration times by volume. Concentration is 0.5 moles per liter. And our volume is 50 milliliters. Divide by 1,000 to change it into liters. So 0.05 liters. We get 0.025 moles. This is moles of lead 2 nitrate. We want to know the moles of lead. But remember, I told you to remember it's a 1-to-1 ratio. So we can sort of skip our sort of molar ratios in stoichiometry here, since it's 1-to-1, and say that's how many moles of lead ions we have. But then we're going to put it, when we mix it, into a new volume. So in our new volume, we can calculate its new concentration by doing N over V. So we have our moles, 0.025, divided by our new volume. So when we add 50 milliliters to 25 milliliters, the new volume is 75 milliliters. Add them together. Divide by 1,000, put it in liters. And we get our new concentration of our lead ions, which is 0.33 moles per liter. So right over here in our ice chart, I'm going to write 0.33. Now we need to do the same for iodine. Now you can say, if you remember this equation, C1V1 equals C2V2, you can use that one. That'll work as well to figure out what your new concentration is, but that only works as long as your molar ratios are 1-to-1. So make sure you understand how to do it this way, just in case you have a situation where your molar ratios are not 1-to-1. But in our second scenario, our molar ratios were 1-to-1. So let's go ahead and see what that looks like. So we have, we can do C1V1 equals C2V2. We'll do it for NaI. So we have our concentration of 0.025 moles per liter, or just molar, times our volume of 0.25 milliliters, so change it into liters, divide by 1,000, is equal to our new concentration times our new volume, which is 0.075. So essentially, to solve for C2, we are just taking concentration, timesing it by our old volume, so 0.025. Remember, capital M is just moles per liter. I just got lazy. Moles per liter times our original volume, divide by our new volume. And in this case, we get 0.0083 moles per liter. So we can go ahead, I'm going to add that into our ice chart. So 0.0083. Now we can get back to the question of, will a precipitate form? Because we know how much ions we are starting with. The question is that more than the saturated or the equilibrium amount? Is that supersaturated or unsaturated? So we can look up what that equilibrium amount is. So you can look up the KSP value on a table, right, which typically chemistry students will have a table of solubility product constants. And for lead to iodide, it is 8.5 times 10 to the minus 9. So if these concentrations are perfectly at equilibrium or perfectly saturated, when I apply equilibrium law to them, you would get this number. What we're going to do then is try a trial quotient. We are going to apply equilibrium law with these concentrations to see how they compare with the equilibrium constant. So to apply our equilibrium law, we've got the concentrations of Pb to the power of 1, because our coefficient here is 1, so power of 1, times the iodide concentration. This is coefficient of 2, so we're squaring that. So let's plug in our values, see what we get. So we've got 0.33 times 0.0083 squared. And when we do that, we get 2.3 times 10 to the minus 5. So clearly these two numbers are not the same. So this is not at equilibrium. In fact, Q, if you look at the exponent, don't focus on the number, look at the exponent, Q is much bigger than KSP. That would mean that these concentrations are much higher than they would be at equilibrium. So equilibrium will then favor the reverse reaction, creating a precipitate. So therefore, a precipitate will form. Okay, so when Q is much, much greater than KSP, it's supersaturated and you get a precipitate. If it happened that it equals KSP, that is your saturation point, it's at equilibrium, no precipitate, because it's already at the maximum amount that you can have dissolved. Although if you were to add just a tiny bit more, then you would get a precipitate. Okay, if it is less, then it's unsaturated and no precipitate will form. So that's how you analyze that problem. I hope this tutorial helped. If you have any questions, let me know in the comments. And if you want some resources, like my course packs I have available for different subjects in high school that you can download for free in the description. Thanks for watching, and I'll see you in the next tutorial.